Okay, 22.3 Aldol reactions. Okay, so far we're starting out with a new word, Aldol. And so I'm going to start, before we even get into it, so let's look at that for a second. Remember, you know what an aldehyde is, right? That's an aldehyde. And you know what an alcohol is, right? There's an alcohol. Agreed? Okay, so recall that when an aldehyde is treated with hydroxide or an alkoxide, in equilibrium forms where significant amounts of both enolate, what's that? Stop. Enolate, right? Remember an enolate was this? Remember that? Okay. Where an enolate and an aldehyde are present. So you've got some equilibrium that looks like this. Right? Now this isn't balanced, okay? I realize that. There's a hydrogen missing. But we can say, all right, that's essentially what we're talking about. That's what this is talking about. So recall that when an aldehyde is treated with hydroxide or alkoxide, in equilibrium forms were significant amounts. So we've got both of them in the solution, right? Now, if the enolate attacks the alkoxide, what does that look like? I'm going to go along with this because it's going to be really easy to get lost in these terms. It's going to be a long lecture. All right, so what it's talking about this is how you should be doing your notes. I'm not sure if this is going to be an equilibrium or a one-way reaction. Let's talk about that. Well, let's do it like this for now. Let's go back here to this. All right. So if the enolate attacks the aldehyde, do you see how I'm being active with this lecture that I'm getting off the slide, right? So I'm stopping and making notes and figuring out what's going on. So if and looking at this stuff, right? So I'm being very active. I'm grabbing it. So if the enolate attacks the alkoxide, or the aldehyde. Let me go back here and look at this. To be a little more active. My vocabulary is not with me today. To be a little more active, I could have drawn this out. That would have been a good thing to do. Okay? Now, but I'm not going to draw that for you. So if the enolate attacks the aldehyde, all right. If the enolate, watch this now. If the enolate attacks the aldehyde, so here's my attacker, right? And there's my vulnerable carbon. Boom. Okay, so what's that going to give me? It's going to give me a new bond here between that a new bond between that and that. Now this is a little ugly, so I'm going to redraw it. 1, 2, 3, 4, 5. Oh wait, that's not how enolates attack. That's not how they attack. We learned how they attack in a different one. Now I'm going, okay, yeah. Actually, that was an inadvertent mistake on my part, folks. I haven't woken up yet. So I saw the negative here, saw the lone pair of electrons, and just made that the attacker. But that's not how enolates attack. Go back and look at section 22.2. Go look at it. Where's the attacker? Ah, the attacker is really here. Okay? So no, we don't have a new bond there. Boom. Okay. So this, because that's not the one that does the attacking. Really, what does the attacking? Oops. This is in resonance, right? Remember this? It's in resonance with that. Man, I haven't woken up yet. That was a Freudian slip. That was probably good that I made that slip because you can see how easy it is to do that. But I go back to section 22.2, and I remember, wait a second, it's really the carbon that does the attacking. So these are the electrons here that are really doing the attacking, which is what I said here. Same thing. Those are the same thing. Okay? So if that's the case, now I really have a new bond between 1, 2, 3, and 4. Okay? I'm going to redraw it now. 1, 2, 3, 4. Okay? Now on my 2 carbon, I guess I should do this in blue to keep consistent. On my 2 carbon, 1, 2, 3, 4, 1, 2, 3, and 4. On my 2 carbon, I've got my sort of alkoxide there, right? This is not there, so I don't have to worry about that. I've got a bond between 2 and 3. It's my red numbering system that's legit. Get rid of that. Okay? It's my red numbering system. 1, 2, and a 3. Got a new bond between 2 and 3, which is cool. That's where my electrons went. And 4, now what happened with 4 was these electrons came back down, right? Because this was the one that was doing the attacking. Agreed? Wow, scary. Okay. Now, obviously, we're going to see this in the slide when we go next, or maybe the slide after it. Go back to the PowerPoint, or go back to it. But I want to be active when I'm doing this. I want to think about what is meant by this. Okay, so we said that the enolate attacks the aldehyde. So all this comment here that I've got here, all this stuff here, came from that statement, right? When I said that, I went, okay, perfect time to review it. So I go back and look at that, and now I'm going to make sure I've got all the same atoms here. 1, 2, 3 atoms, 4, 5, 6 atoms. 1, 2, 3, 4, 5, 6 atoms. This is neutral. This has got a negative on it. This is neutral, and that's got a negative on it. So this is correct. All right, now I'm ready to go back and look at the PowerPoint. Okay, so if the enolate attacks the aldehyde, an aldol reaction occurs. All right, so I didn't have it balanced before, so I see that if I'm doing this with trace amounts of sodium hydroxide, I've got water in solution, I can protonate it. That's exactly what I have on my other. Let me go back and look at that, show you, prove it to you. If I've got this, and I also have water in solution, right? Can you see what's going to happen? Boom, boom. And that's exactly what I have over here. Look at that. Boom. Okay? Now, you see that there's 2 equivalents of this. So this is not balanced. This only has 3 heteroatoms in it. This one's got 6 heteroatoms in it. I'm not counting hydrogens, okay? So the product features both aldehyde and alcohol groups. All right, so which we knew because we predicted it. Note the location of the hydroxide on the beta carbon. Okay, so let's go back here. Let's go back here. This is the, let me change colors here. This is the carbonyl, right? So here's the alpha carbon, here's the beta carbon, here's the gamma carbon, right? Notice the location of the, okay? And this is called, watch this, a beta hydroxy carbonyl, right? Because we have a beta, we have a hydroxy on the beta carbon. All right. So note the location of the hydroxyl on the beta carbon. All right, we're gonna roll. That was a long slide. Now we're gonna go back and review the mechanism. It's 100% review, 100%. Let's go here. This was from section 22.2. Okay, hydroxide takes proton. Proton leaves the electrons behind, and we get a nucleophile. Okay, now this is resonance stabilized, or rather, I'm sorry, this is resonance stabilized with what? Pause the video and draw that structure out. Very important. If you're asked to do the mechanism on this, and if you don't have this, you're not going to get full credit. I'm sure of it. All right, very important. So now that we've got that, though, this is the attacker. there's where I made my mistake before on the previous one. I caught the mistake because I knew we weren't making an oxygen-carbon bond because I had that memorized. Okay, so we learned in section 22.2, it's the carbanion that's going to be doing the attacking. So boom, boom. All right, and then we get, all right, and this entire mechanism I drew on my sketch pad on the whiteboard, which you saw before. All right, so excellent. This is the Aldol mechanism. And can you see why we would call it Aldol? Aldol. Okay. Oops. Oh, wait, the D goes with that, sorry. This doesn't have any erase function, so, or not a nice one. All right. Okay, so this is the mechanism. Memorize it. This is one that's missing. This part right here is an important aspect of it. So Klein gives you, where's my marker? Klein gives you the linear, sort of the straight talk here, but you need this. And I'm going to put this in brackets here to help you remember that, or to help you see it. But you need that structure there, or else you won't get full credit for it. All right. It would be good, I think, even better to learn this if you ask yourself, why am I not getting full credit for this? What's the reason for that? Okay, let's move on. The Aldol reaction is an equilibrium process. It generally favors the products, okay? All right, not always. What does that mean? That means we can push it the other way. You've seen that before. We can push this the other way, and the one way to do that is to fiddle with Le Chatelier's principle. How might temperature, good question. How might temperature affect the equilibrium? Okay, so a similar reaction for a ketone generally does not favor the beta hydroxy ketone product, and I'll show you why. So first of all, if you do a ketone instead of an aldehyde, you're mostly going to go in this direction, right? The equilibrium favors that direction, and I'm going to ask you to pause the video here and show the mechanism for the retroaldol reaction. Show the mechanism for this reaction. Pause the video and show the mechanism, and then go practice with Skill Builder 22.2. Okay, so predict the products for the following reaction and give a reasonable mechanism. Be careful of stereochemistry. I'm going to ask you to pause again here, draw it out, and bring your notes to class. Okay. When an aldol product is heated under acidic or basic conditions, an alpha-beta unsaturated carbonyl forms. This is called an aldol condensation because we're giving off water. All right, so we're condensing water out of it, and it turns out that this is going to be super common. And we've got now an interesting moiety here. Look at this little interesting motif. It's conjugated, right? You see that? So such a process is called an aldol condensation. The elimination reaction above is an equilibrium, which generally favors the products. It doesn't show it's an equilibrium here, but it would be interesting for you. It is an equilibrium, generally favors the products. It'd be interesting for you to show the entire mechanism back and forth. It'd be great practice going back and forth, okay? So why would it generally favor the products? And so there's a hint here to consider enthalpy and entropy. There's two aspects here. All right, the elimination of water can be promoted under acidic or basic conditions. And again, I'm going to ask you to practice the mechanism for both of these. Eliminate water, and you've seen both of these eliminations before. Just go E2. Okay, I'm not going to give you those mechanisms here, but I want you to practice them. Consider going back to chapter 8. How was it? 8 we did eliminate. I don't remember what chapter it was. Maybe chapter 8, where we did eliminations. Both an acidic elimination and a basic elimination. All right, when water is eliminated, two products are possible. Oops, thought I fixed this. Keep. A little ugly there. Okay, 2. When water is eliminated, 2 elimination products are possible. Which is likely to be the major product? And use the mechanism to explain. Wow. I gave you a hint in a previous slide. Which is going to be major? And why? Wait. Those are the same thing. Oh, man. Oh, those are the same thing. This is a mistake. Forget this, folks. I'm sorry. I don't really have time to make a nice video. I need to get this material presented. So I'm sorry. These 2 structures are the same thing, except one is missing a carbon. So this is wrong. All right, this is wrong. But make up your own structures. When water is eliminated, 2 products are possible. What are the 2 products? 2 products are possible. What are the 2 products? And then you tell me which is likely to be the major product. Okay. This is a mistake. Sorry about that. But you do get 2 products possible that are different from each other. Draw those out, please. Bring them to class. If you don't know, draw at least one of them out. And then you really should work through the mechanism. Okay, because the aldol condensation is favored, often it's impossible to isolate the aldol product without elimination. So in other words, if you do an aldol condensation with this guy, acetophenone, then you're going to get this. This is the aldol reaction, but you can't stop here. It's not isolated. It's going to condense water. All right. So condensation is especially favored when extended conjugation results. Where is the extended conjugation in the above structure? Where is the extended conjugation? What? Pause the video and draw that out, the extended conjugation. All right. At low temperatures, condensation is less favored, but the product is still often difficult to isolate in good yield. All right, so I think most of the practice problems we're going to see are going to automatically give the condensation product, right? So even at cool temperatures, we're still going to only get 20%, right? At cool temperatures, what's going to be the 80%? What is that going to be? Now go practice with Skill Builder 22.3. Okay, predict the major product of the following reaction. Draw this out. And if you don't like it yet, take your time and do the mechanism. Okay, substrates, this is real super interesting. Now watch this. Substrates can react in a crossed aldol or mixed aldol reaction. Predict the 4 possible products in the reaction below. What are you talking about, crossed aldol? I'm going to give you, pause the video here and make some notes on this. After you've made a guess, then I'm going to tell you, I'm going to give you a hint. Go pause it now. Okay, I'm going to suppose you've paused it. Now I'm going to say, watch this, crossed aldol or mixed aldol reaction. What this means is, if you add sodium hydroxide, where's my marker? If you add hydroxide to this, then you're going to get 2 different enolates. One of them is going to be from here. Right? And this, of course, is resonance stabilized with something else. And the other enolate is going to look like this one. Right? And that's going to be resonance stabilized with something else, okay? So now that you've got this enolate, this is a pretty big hint, can either attack one of these guys or one of those. And it's going to attack both of them, right? Because we have a bunch of them. We've got billions and billions and billions of these things. So when this enolate is formed, it's going to see both this propanol and acetal, right? Or we call it acetaldehyde, I guess. This is propanol and ethanol or acetaldehyde. Okay? So, such a complicated mixture. You need to, and if you don't have that yet, you need to pause the video now and go through that. You need to. You won't get this well if you don't do it. Alright, such a complicated mixture of products is not synthetically practical. Why is that? We've asked this question many times in these videos. So such a complicated mixture of products is not very practical. And then after we asked this question, we always followed up with something else. And what is that? We followed up with a method to make it synthetically practical. Here it comes. Practical crossed aldol reactions can be achieved through one of two methods. Number one, you can make it so that you have no alpha protons. So the only enolate you can form is going to be from this one. Right? Right? That's the only enolate you can form because you don't have an alpha hydrogen over here. And so that's going to then be more likely, you won't get one of those products. Two of those ones, okay? That you predicted in the previous slide. Okay, one of the substrates is relatively unhindered and without alpha hydrogens, and then the way that you push this even further is that you make sure that you have a vast majority of this while you're dripping this in, right? You've got 1 mole of this and 1,000 moles of this, right? And that means that every time this enolate is formed, it's more likely to find one of these guys, right? Because it's surrounded by them. Or another way is just to drip this stuff in, just to drip it in. Little by little. This is a cool technique. It's difficult as an undergraduate student to think about the practical implications of this stuff, but frankly that's where it gets fun, is when you say, well, okay, what's it mean? What kind of puzzle can I solve with this? And so we spend so much time talking about the theory, it's difficult to appreciate the practical stuff. And this is a little practical point here, which students oftentimes just ask me not to even mention to their own peril. One of the substrates is relatively unhindered without alpha protons, so that's one method that we can get across to aldol. Okay, so here's another example of one that has no alpha hydrogen. No alpha hydrogen, right? That's one way to get across to aldol. And then the other way, well, I already mentioned. I mentioned this. Sorry, I couldn't resist. Is to add one substrate in dropwise. And we add it in with a really strong base, LDA, which we mentioned before. Draw the structure of this out now. Pause the video and draw this structure. And write out the full name. Forming the enolate first. Subsequent addition of the second substrate produces the desired product. Okay? What are we talking about there? A little subtle. Okay, now go practice with skill builder 22.4 and come back. Okay, describe a synthesis necessary to yield the following compound. Now, I'm going to pause the video now, and then I'll come back and I'm going to give you a hint. If you haven't paused it, if you're not sure what I'm saying, pause it and make a guess, right? Okay, I'm going to suppose you did pause it, and I'm going to give you a hint. The hint is, I'm looking at this stuff, and first of all, since I know I'm talking about aldol condensations recently, where's my marker? I'm going to go ahead and go, oh, here's my conjugated system. There's my alpha, beta, right? Alpha, beta, sorry, alpha beta conjugated system, right? So what I'm going to do is I'm going to go backwards. I'm going to draw this. One, two, three, four, five. 1, 2, 3, 4, 5. Okay, I'm good there. So it's the beta that has the hydroxy on it, right? Okay. Now I can work my way backwards and say, all right, well that came one, two, three, four, five, or 5. That came from that. Okay, this now must have been my enolate, right? That must have been my enolate. And I'm going to go back from there. Okay? All right, pause the video now and keep working that back. All right, I'm going to move on. I'm going to suppose you paused it and worked with it. Bring your notes to class. Nope, 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 nope. Cancel. Got one more slide to go. Okay, now finally cyclic compounds can be formed through intramolecular. We've done intramolecular several times now, but we can do the same thing with an aldol. And this is cool. Very cool. And actually it's going to warm us up for the next couple sections too. So cyclic compounds can be formed through intramolecular aldol reactions. Wow, look at that. So 1, 2, 3, 4, 5. Alpha, beta, or coming from the other way, that's the alpha, right? All right, this is a little difficult. I'm going to go with a different numbering scheme. Well, difficult for me because I'm not thinking real clearly, but I've just waking up. 1, 2. Okay, that'll be 1, 2. Okay, so I'm going to call that. Looks like that's where my alpha beta unsaturated was, right? You see that? I'm going to write over the top of that. Alpha beta. So this is my other one. That's my alpha beta. This must be my, just a second here. That's difficult to see, isn't it? Alpha beta, I gotcha. Okay, so my alpha beta unsaturated, this must have been my enolate. That's a toughie. Draw the, oh, here's the answer right here. Okay, that's a toughie. You see, you're going to have to do some math on that. I sort of am thinking through it out loud on here. You're going to have to do some backwards figuring, and it's not easy. But your alpha beta unsaturated is going to come from the one that was the attacker, right? This was, I know I'm speaking in circles, especially if you're barely understanding this. You got to go back and practice these mechanisms. That was the erstwhile enolate. Erstwhile. It's the first time I've ever used that word in an organic lecture. But that means that's the guy that used to be the enolate right there, okay? Go back and practice the mechanism. Prove to yourself that that's what it is. You see it here. There's the mechanism. I mean, there's the enolate, right? Okay. Okay, recall 5 and 6 membered rings are most likely to form. Why is that? That's going to be key, I think, in one of the practice problems here. Shoot, we could have a different dione, and that's one of the most common quiz questions for this, right? It's a different dione that will give you a 5 or 6 membered ring, or like a 7 or 8 or a 3 or 4. What am I talking about? Practice that and see what I mean. And then go and do conceptual connection checkpoint or conceptual checkpoints 25 to 27. All right, that's the last slide for this lecture. That's rough. You need to practice this. It's going to take some time. Best wishes.